Before looking into the sigma notation, we first need to understand the difference between sequence and series. So sequence is a list of numbers in a specific order. So something like 3, 7, 11, and 15. So they all fall in one order. A series, on the other hand, is the sum of a list. So if you take the sequence and instead of having commas in there, you'd have addition in there. So you're adding the list of numbers. Now it gets a bit tedious to add the numbers there, so as in write the long list of numbers. So we want to shorten this expression. I'm going to use the sigma notation to denote this long set, this sum of numbers. So we sometimes use Sn to denote the sum of the series. This is not the sigma notation, but it is the notation we say for the sum as well, so for a series more specifically. So if I'm adding, for example, 13 numbers or 13 terms, so in this case my n is equal to 13, so I can say, oh, so the sum of 13 terms is such and such. So this is the sigma notation, and it's a capital sigma. So you need to understand and recognize all the parts. So we first start with the index. So this is what gets replaced, the n variable. So this value will keep on changing in the expression here. So what the bottom part tells you is what the lower limit is. This is the first value to be substituted. It's also called the floor. And then the top part tells you the upper limit, the ceiling. So you're going to keep on, you're going to add 1 and then 2 and then 3 and then 4 until you get to the value k. Now to note that it doesn't always have to be, not always 1. So it can start at a negative value, it can start at 0, it can start at 5. But they move in integers. So if I start with 5, then the next value is going to be 6, 7, 8, and so on. So they're going to move into integers until you get to your ceiling. And then this is the expression where you're going to do the substitution. And we're going to do enough examples to show how you can do the substitution. Sometimes there's no direct substitution in there, but wherever you see the n, that's where you substitute your direct value. So this letter tells you what letter should be substituted by a number. We have this example, and it's telling you that n starts at 1 and the ceiling is 5, and this is the expression that you substitute in. So 3n minus 2. So what we're going to do is we're going to keep on adding this every single time, but every time we repeat the expression, we're going to substitute a different value for n. So we're going to start with 1 and then 2, 3, 4, and then continue until 5. So this is the expression to make it a bit clear. So this is the first one. I'm substituting 1 in there. I'm adding it again, but I'm substituting 2 in there. I'm adding it again. I'm substituting 3, 4, and then 5. So I could do this, simplify the expression, and then you're going to get 35. So instead of telling you the long list of numbers you need to add, this is a more shortened way of explaining this sum. Now, sometimes we don't want to have a ceiling of 5. Sometimes we're going to have an infinite series, and we can write the upper limit as infinity. So that's definitely doable. The sum of series that go to infinity are special expressions that you can actually solve at this level of the course. Using a calculator, you can actually put this sigma notation in your calculator. It's good for a calculator paper where you want to check your answer. So on the GCSE, you're going to go on math, and you're going to go all the way to the bottom where it says summation. You're going to press on that, and then you are going to have this pop up, and what you're going to do is you're going to place the x in there, so that's the variables here, so this is the button, and you're going to start with your floor, ceiling, and then add the expression. Make sure the expression is inside the brackets. Once you do that, obviously make sure that you match the variable here, so we have n's that match, like that's an x in the calculator here, and it gave me a sum of 35. So a few more examples. This is where the floor is not a 1, so I just want to show how that is, and also when you have different variables. So if you notice there's an x here, but my summation only tells me that the substitution will occur with n only. So we have the first one, I'm substituting 2, and then the second one, I'm substituting 3, third one, I'm substituting 4, and then the last one, I'm substituting 5. Simplify the expression, I'm going to get 54 divided by 2x, and then you can simplify it further, and it's going to be 27 over x. So it is fine to end up with a variable or an unknown here value. It is okay, just making sure that you substitute only the value that's mentioned in the sigma notation, and they always tell you the value. There's no sigma notation that starts with just a number here, unless it's made clear from the beginning what has to be substituted. Now, for powers of -1, or when you have multiple substitutions, so I'm combining different situations here in one example. So powers of -1, and not just -1 actually, it's powers of any negative number. So these are special, and hopefully you're going to notice a pattern here. We also have multiple substitutions. So we have a substitution as a power, and we have a substitution as a multiplication with 2, and this will end up being 4. Now what I want you to notice is what happens with the odd power and the even power. So notice with every odd power, so the 1 and the 3, we are getting a negative value here. So we're getting a negative expression. And with an even power, we are getting a positive expression. Now you have to be a bit smart. This is a simple example where it's just -1. If there was another negative here next to the 2n, then the operation is going to be more different, so you have to think about it. But if you start with basically understanding that if you have this expression, then it's going to be a positive for an even power of n, and it's going to be negative for n, when n is even, and then negative when n is odd. If you have something like -2 to the power of n, you can actually simplify this as -1 times 2 to the power of n. Using the powers of indices, rules of indices, you can expand this, and they're both powers of n. So all you'll have to deal with is this -1 to the power of n, because you know how -1 to the power of n behaves using this rule. So I would recommend you pause the video right now, try to go through this. What I want you to do is understand how the summation is occurring, shown for these series. So the first one, we're multiplying by powers of 4. So we're getting powers of 4 every single time. So it's 4 to the power of n. And the series continues infinitely. So we have, this is where the upper limit is infinity. The second one, it's an arithmetic series, hopefully you've noticed. And I could find the general formula for the arithmetic series. It's 4n plus 4. So I'm just adding this every time. Now, there is a different way of writing this, so if you got a different answer, that's completely fine. The different answer will start with a different floor, but the ceiling is still infinity. So yes, sometimes we can get different expressions for the same sigma notation. We then have this as -2, but there's no substitution that goes on, and there's only 8 of them, so this is what the n equals to 1. This is what these do. There's no substitution here. It just tells you that you have to repeat the summation 8 times. The part D is, hopefully you've noticed the alternating signs. So that means we have a -1 power that's changing, -1 that's to the power, and then the denominator is increasing by 1 every single time, starting with 1 going to 100. And then you need to be smart about how to make sure that -1, that the expression is always negative at the odd expressions. So we can place 1. If it's the opposite, if it was negative at the even expressions, then you want to put a n plus 1 or n minus 1 to change it. And then the last one, you have, you should notice that the m has to be there with no substitution in there. And the m changes, it increases in power, but starts with 6. So I can start my floor at 6. But then the coefficient is square numbers. So, but the square number of a higher power than the power of m, a higher value than the power of m. So if this is 6, then this is 7 squared. If this is 7, this is 8 squared. I can do n plus 1 squared m to the power of n. Up until 10. Keeping in mind, again, same thing with the second one, you can do a completely different one where it's n squared m to the power of n minus 1. So you can actually write different expressions for the same sigma notation.